Welcome back to the deep dive. For years, there's been so much buzz around these massive AI models.
Mhm.
We're talking models with hundreds of billions of parameters, like
Yeah.
GPT-3 or Gopher.
Right, they're real giants.
Exactly.
Mhm.
And the common wisdom, kind of the mantra, has always
Yeah.
been the bigger the model, the better it performs. It seemed like a straight line, didn't it?
It really did.
But what if we told you that actually many of these incredibly powerful large language models might be, well, undertrained for their sheer size?
It's a really counterintuitive idea, isn't it?
Absolutely. It sort of challenges a fundamental assumption that's guided AI development for years now.
It definitely does. A big challenge.
So what exactly are we hoping to uncover today? What's the central question we're tackling in this deep dive?
Okay, so our mission today is to unpack why these current massive models might actually be underperforming, or maybe, let's say, suboptimal.
Suboptimal, okay.
And then we'll introduce this really groundbreaking finding from DeepMind, and most excitingly, I think, show you a model called Chinchilla.
Ah, Chinchilla.
Yeah, and Chinchilla fundamentally proves that sometimes less size can actually mean much more performance and more efficiency, too.
All for the same computational cost.
All for the exact same compute budget. So yeah, get ready for some genuinely surprising takeaways here.
Okay, let's dive in then. Let's set the stage first by talking about this era of bigger is better
Yeah.
and what you called its hidden flaw.
Right.
For years, the undisputed mantra in large language model development, LLMs, has been to just scale up the number of parameters.
Keep making them bigger.
Yeah, we've seen these titans emerge, like GPT-3 was at 175 billion parameters,
Mm-hmm.
Gopher at 280 billion, and even Megatron Turing NLG topping out at a staggering 530 billion parameters. It really felt like a race to build the biggest possible brain.
It did. But what's fascinating, or maybe troubling in hindsight, is that while these models grew exponentially in size,
Yep.
the amount of training data they actually saw remained relatively constant for many of them. Often it hovered around, say, 300 billion tokens.
Huh. Only 300 billion tokens, even as the models got vastly bigger.
Pretty much. And this practice, it wasn't just random. It was heavily influenced by earlier, quite respected work. That work basically advised pouring most of your increased computing power into making the models vastly bigger,
Right.
while only modestly increasing the training data. So the wisdom was kind of size first, data second.
So the conventional thinking was basically throw more compute at making models bigger, but the data side wasn't really keeping pace.
Exactly.
And this, of course, had massive implications for cost, didn't it?
Oh, precisely. I mean, training these colossal models requires immense computational resources and energy, too.
Yeah.
It's so expensive, in fact, that it's usually only feasible to train them once. You get one shot.
Like a rocket launch analogy you mentioned. One go.
Exactly. You get one shot at getting it right. And this makes nailing down those foundational hyperparameters, like the model size versus the training data amount, absolutely critical right from the start.
Because if you get that wrong on a project, this scale,
Well, you've potentially wasted a huge amount of resource.
that's the multi-million-dollar question right there.
Yeah,
So if you're only getting one shot, what is the optimal way to use that compute budget?
right.
Which brings us to the core question, I guess. Given a fixed computational budget measured in FLOPs, right, floating point operations,
Yeah, the total compute power.
how should you optimally balance the number of model parameters, so the model size, and the number of training tokens, which is the amount of data it learns from?
And this is exactly where the DeepMind team made their breakthrough. They set out to answer precisely that question.
Okay.
They trained over 400 language models, not just a few, over 400,
Wow.
with sizes ranging from a, relatively modest 70 million parameters all the way up to over 16 billion parameters.
A huge range.
And crucially, they trained these models on data sets ranging from 5 billion tokens up to over 400 billion tokens. So they varied both dimensions significantly.
Okay, so after all that really intensive experimentation, what was the big reveal? The counterintuitive finding that flipped the old thinking on its head.
The real aha moment, the thing that genuinely surprised the research community, was this. For optimal training efficiency and performance,
Yeah.
model size and the number of training tokens should be scaled equally. They need to grow in lockstep.
Equally. So not size first.
Not size first. For every doubling of model size, the number of training tokens should also double. It basically means the data is just as important as the model architecture itself.
Wow, that's a really powerful statement. How did they arrive at such a definitive conclusion when the previous wisdom pointed elsewhere?
Well, they didn't just, run one experiment and call it a day.
Yeah.
They attacked this question from 3 completely different angles. It's like triangulating the result.
Okay, what were the angles?
So, first, they did what you might expect. They fixed different model sizes and then varied the amount of data each size saw, looking for the performance peak.
Makes sense.
Second, they looked at something called isoflaw profiles, basically plotting different combinations of model size and data that would cost the exact same amount of compute to train.
Okay.
To find the sweet spot on that fixed budget line.
Clever.
And third, they used some pretty advanced statistical modeling. They call it parametric loss function fitting to model the relationship across all their hundreds of experiments.
And all 3 pointed the same way?
Every single approach pointed to the same, quite surprising answer.
Yeah.
You need to scale model size and the amount of data equally for optimal training. A 1-to-1 scaling.
Okay, so this isn't just some academic detail buried in a paper. How does this actually change things for us, as users or observers of AI? What does this mean for you listening right now?
Well, the big implication from their analysis was that existing large language models, the ones we were just talking about, like GPT-3 and Gopher, were, and I quote, considerably oversized for the compute budgets they were trained on.
Considerably oversized, meaning?
Meaning they spent too much of their budget making the model big and not enough feeding it data. Think about it. A 175 billion parameter model, like GPT-3,
Yep.
if it were built using this new optimal strategy, should have been trained on over 4.2 trillion tokens.
Trillion, not the 300 billion we talked about.
Exactly. Over 10 times more data than was typical.
Wow.
It's like, building this massive supercar engine, but only putting a tiny fuel tank in the car. You're just not getting your money's worth performance-wise.
That's a fantastic analogy. So the old way was go big or go home, but the new way is more like go smart, use your data, then go home because you've saved a ton on compute.
Something like that, yeah. And to really prove this radical hypothesis, they didn't just publish the analysis, they trained a new model.
Called Chinchilla. Tell us about Chinchilla.
That's the one. So, based on their new optimal scaling laws, they predicted that for the exact same computational budget used to train Gopher, remember, Gopher was 280 billion parameters.
Right, the big one.
An optimal model should actually be around 4 times smaller, somewhere in the, say, 40 to 70 billion parameter range. But critically, it should be trained on 4 times more tokens.
So smaller brain, much bigger library.
Precisely. This was the real acid test for their theory.
And Chinchilla specs reflect that perfectly, right? It's a 70 billion parameter model, so much smaller than Gopher.
Yep, right in that predicted range.
But trained on a truly massive 1.4 trillion tokens.
4 times the data Gopher likely saw, roughly.
And the critical part, it consumed the exact same compute budget as Gopher.
Exactly the same FLOPs. It was designed as a direct apples-to-apples comparison. The old recipe versus their new data-centric recipe.
So, the moment is truth. How did Chinchilla perform? Did the smaller model with more data actually win?
The results were pretty undeniable. Chinchilla uniformly and significantly outperformed Gopher. And not just Gopher. It also outperformed even much larger models like GPT-3, Jurassic 1, and that huge Megatron-Turing NLG model across a whole wide range of downstream evaluation tasks.
So it wasn't just a fluke on one task, it was consistent.
Very consistent. It really hammered home their hypothesis.
Okay, let's highlight some of those key victories. What were the standout results?
Well, take the MMLU benchmark. That's a tough one. Tests a wide range of academic subjects, basically a general knowledge test for AI.
Right.
Chinchilla achieved a state-of-the-art average accuracy of 67.5%. That was a remarkable 7.6% absolute improvement over Gopher.
7.6%. That's huge in these benchmarks.
It really is. And get this. That score actually surpassed the expert forecast for what the state-of-the-art accuracy would be in June 2023.
So it was ahead of its time, you could say. It saw the future of AI performance.
In a manner of speaking, yeah. Then, in reading comprehension on datasets like RACE and RACEM, Chinchilla showed improvements of over 10% compared to Gopher. Just flat out better at understanding text.
10% is massive, too. What about truthfulness? That's a big concern.
Good question. On Truthful QA, which is specifically designed to measure how factual a model's responses are, Chinchilla showed a significant 14.1% improvement in zero-shot accuracy over Gopher.
Zero shot meaning it just knew it. No special examples.
Exactly. No specific fine-tuning for that task.
Hmm.
It just answered more factually right out of the box. And this strongly suggests that better modeling of the pre-training data training longer on more data leads directly to more factual responses.
Yeah, it makes intuitive sense. More learning, better facts.
Seems so. And beyond just the raw performance numbers, there's this huge efficiency bonus we mentioned.
Right, because it's smaller.
Exactly. Being 4 times smaller than Gopher means Chinchilla needs substantially less compute for things like fine-tuning it for specific tasks or just running it for inference, actually
Right.
using it to generate text.
Which makes it much easier to actually deploy and use, right?
Yeah.
Even on smaller hardware.
Absolutely. It greatly facilitates downstream usage and significantly reduces those ongoing energy costs and computational demands. It's genuinely a win-win.
Yeah.
Better performance and cheaper to run later.
So this deep dive really does shift our perspective, doesn't it? It's clear the future of LLM scaling isn't just about this relentless drive for more and more parameters.
Not solely, no.
It's really about an increased focus on gathering and using larger data sets. But critically, as you said, ensuring that data is also high quality.
That's absolutely the key takeaway. Larger, high-quality data sets seem crucial for the next steps in scaling effectively.
And thinking about these massive data sets, trillions of tokens, raises other important questions too, right? Like societal impact, bias.
Definitely. And it's worth noting what they found there. For instance, on bias, even though Chinchilla was trained on similar data to Gopher,
Okay.
it actually showed improvements in handling gender bias. They tested it on the wino-gender dataset. And Chinchilla resolved pronouns more accurately across all categories: male, female, neutral. And there was a notable 10% improvement specifically on female gotcha examples. Those are sentences designed to contradict typical gender stereotypes.
So the more optimally trained model was actually less biased in that specific context. That's really interesting and positive.
It is quite interesting. It suggests better training might mitigate some biases, though it's obviously complex.
What about other areas like toxicity? Did training longer make it more prone to generating harmful content?
Also interesting, despite its overall improved performance, Chinchilla showed basically a negligible difference in toxicity levels compared to Gopher when generating text without specific prompts.
Really, no major change.
Its mean toxicity score was incredibly close to Gopher's. So this suggests that simply improving the core language modeling quality doesn't automatically make a model more toxic. That's a separate challenge, it seems.
Okay, but the challenges definitely remain. So let's recap the big aha moment from this deep dive then. We've basically seen that the race for just massive model parameters, bigger and bigger models, might have been missing a really crucial piece of the puzzle.
Which is?
Equally massive and critically high-quality training data.
Right. Chinchilla really showed us that optimal efficiency and genuinely superior performance come from a balanced approach. And often, that balance means smaller models trained much, much longer on much more data.
Which leads us perfectly into a final provocative thought for you, our listener, to chew on. If this next frontier of optimal LLMs really does require datasets measured in the trillions of tokens, and if responsibly curated, high-quality data is absolutely paramount, what happens when we start running out of truly novel high-quality data to actually feed these models?
The data wellspring.
Could we hit a kind of data ceiling? And if so, how might that reshape the very future of AI development and how we even think about artificial intelligence?
That's a really deep question. What happens when the best data runs out? Something to definitely mull over.